I'm John McCutcheon. My talk is going to be pretty low level, so I hope you enjoyed Seth's talk, which was nice and high level, gooey stuff. I'm going to go right into the VM, so let's have some fun. To give you an idea of my background, it's a little bit different to be at a web development talk. When I was in university, I wrote something called iNotify, which is a module for the Linux kernel that does file system notifications. So if something changes on your disk, an event will be delivered to an application. It's used everywhere. Every Android phone uses it. Every Linux desktop, every Linux server is using iNotify. After doing that, I started working at PlayStation, where I helped port Bullet Physics, which is a 3D physics library, to the PlayStation 3, which was a lot of fun because the PS3 has a very interesting CPU architecture with these CPUs called SPUs, which are they're interesting in that they can't access main memory directly. So it takes a lot of juggling to get data and code in and out. So when that project kind of ramped down, I started to just be a go-to optimization guy. So if a game company that was developing for the PlayStation 3 needed to make their game go fast, I would fly out to them and spend a couple weeks working on their code base, speed things up, and then come back. And then I can finally talk about this now. I spent a year and a half studying the PlayStation 4's CPU and GPU architecture before leaving for Google. So it's a little bit interesting. So here I am at a web developers conference, and what brought me here? In particular, it was Dart. I am a C++ programmer just in my blood, and JavaScript is not that much fun for me. I suck at it. It's very difficult. So Dart and its structured approach to web programming it caught me right away. It was like flypaper, and I'm a fly, just stuck. I'm there. WebGL, you can do 3D in a browser now. HTML5. The browser, to me, is an operating system that I want to develop really high-performant, high-end applications in, and I want to make that possible. So it's kind of like this collision of two worlds. I come from a low-level kernel systems programming background, and now I'm coming to the web, and I'm trying to see how I can be helpful. And so I've been experimenting with bringing SIMD to the web. And I'll get into what that is and why it matters. So what is it about Dart that I really liked? Well, first of all, the structure. I love that it has a type system, even if it's only tool visible. My preference would be for a type system that's available in the language, but I'll take a tool-based type system over no type system. Having the tool say, hey, you just called a method that doesn't exist, or you just assigned to some variable that doesn't exist, or you did something silly and warns me right there before I run the code, I need that. I'm a lazy, kind of sloppy guy, and I make a lot of errors. Tools are great. It's class-based and object-oriented, which is, I like the prototype-based language in JavaScript, but it's almost too flexible. It's a lot of fun, but it's this weird sludge, and I'm used to working in a class-based world. Lexical this is huge. Every time I write code in JavaScript, I get bitten by this where because of my own ignorance of JavaScript, I get into the situation where this is the wrong this. And in Dart, that never happens to me, so I really appreciate this. This is kind of a weird one. I love that you require semicolons. I get into debates at work about this. Some people hate that there's semicolons in the language, but to me, it's awesome. Number two, performance. And this is where I just love performance. And this is what really, really attracted me to Dart. Dart is designed to be less permissive than JavaScript so that it can run faster. And anything that runs faster, I'm into. And it comes with a new VM. And this is a new VM written from scratch, designed around Dart and its functionality, and designed to run fast. And so I thought, oh, this is pretty interesting. This opens up new possibilities. Why don't we bring SIMD? Why isn't SIMD on the web? It should be. So before I get to SIMD, let's talk about why Dart can run fast. So in Dart, every object has a static shape. In JavaScript, you can do something like the code up on the screen there, where you have your constructor for my class, and it adds the fields A and B. And then someone goes and constructs it, and then they just add another property to it. You've completely invalidated all of the optimization assumptions around instances of my class. In Dart, that's not possible. Again, Dart is designed to be less permissive, guiding you to having more optimized code. Whole free arrays. JavaScript, you can do something like this, where you have big data, it's an array, and then you add a bunch of numbers into it. And then somewhere later on, you add like big data at 20,000. At that point, the engine says, oh, you know what, you're not an array anymore. You're actually a key value map, where the keys are the indexes into the array. And it becomes sparse, and your data is spread all over memory. It's very bad for performance, and it kind of sucks. In Dart, you cannot have holes in your arrays. If you want a structure like this, you use a map. There is a distinction between growable and fixed size arrays in Dart. So if you know ahead of time that your array will never change in size, you can go ahead and allocate it once, and Dart will make better optimization assumptions based on this fact, like hoisting an array bounds check outside of a loop so that it happens before the loop executes. There's no prototype chain. This is a big performance gain in Dart. So in JavaScript, if you wrote foo equals new some class and you call some function on it, what happens is this. You say, hey, some class prototype, can you respond to some function? No. Well, let's ask your parent, and let's ask your grandparent, until you finally find something in the prototype chain that can actually handle some function. In Dart, you just extract the class ID and you go to the class and you grab the function. It's very fast. There is a distinction between integer and doubles. So the key point here is that double arithmetic is slower than integer arithmetic. And the table at the bottom of the slide here is from a recent ARM processor showing you the cycle latency counts for doing arithmetic on doubles versus integers. And you can see that a double multiplication is 3 times as slow as an integer multiplication, and in addition is actually 4 times as slow. So we're paying this cost every time we do arithmetic in our programs, and it's unnecessary. With a new VM and a new language, we can make better choices that lead to more performant code. So in that case, Dart has both double and integers, and it puts the control into your hands, and you can decide when it's appropriate so that you get the most optimal code. All right, so that's why, this is really like why I got into Dart. I love performance. The web is really attractive to me. I think the browser is a great platform. And it's just very interesting. So I wanted to try something new, and I wanted to try adding SIMD and bringing it to the web. So what is SIMD? I'm going to take a guess that, how many people in the room know what SIMD is? Oh, all right, okay, excellent. I'm in good company. All right, so before we get into SIMD, we need to talk about SysD, which is single instruction, single data. And this is typically what you're doing when you're operating on data in your program. You have a single instruction, like add, and you have a single piece of data. You add the 2 values, and you output the other. SIMD, on the other hand, is single instruction, multiple data. So again, we have a single instruction, add, but we have multiple data. So you're actually adding 4 numbers at the same time with 1 instruction. And a good way to think about this is a vector processor. This is perfect for doing 3D math. So why does SIMD matter? Well, it brings substantial speedups to 3D graphics, 3D physics, image processing, signal processing, numerical processing. It's not a silver bullet. It can't be applied everywhere, but in the areas where it can be applied, the performance gains are huge. So why does it matter to the web? I mean, that's why we're here, right? Well, SIMD can provide substantial speedups to WebGL-based games like HexGL, which is a pretty amazing game, running in a browser, Canvas, animation, other game algorithms, physics simulations. I worked on bullet physics for like 2 years. I would love to see a version of bullet physics running in the browser as fast as it does on a native, in a native application. And SIMD is going to help us get there. So again, why does it matter to the web? Here we have a timeline of video game consoles, starting at the NES, which was my first console, and I love it, all the way up to the PS3. So I'm drawing this line here, and this was console games in 1998. It's also web games in 2013. We are 15 years behind the curve. We can do better than that. So why does SIMD matter? Here is a CPU die diagram of a recent ARM mobile processor, dual core. So you see it kind of mirrored here, right? The top and the bottom are the same structure. So this blue box up here labeled core, that's where all of the integer operations are executed. This yellow box up here, VFP, this is where your double arithmetic is executed. And this red box, neon, this is the SIMD unit that every single one of our modern smartphones has in it, and it just sits idle. It's doing nothing. We cannot touch it from the web. So why does SIMD matter? Well, SIMD requires fewer instructions to be executed, and fewer instructions means longer battery life. And we live in a very mobile world. I mean, I barely make it a day on a charge. And it'd be nice to make it like 2 days, maybe 3 days. And SIMD will help us get here. So here's an interesting thing. Mozilla is actually attempting to use the SIMD coprocessors in all of our CPUs automatically. And so what they're doing is they're looking at the AST of your program and kind of shaking it and looking and saying, okay, actually, right in this one little spot, we could use SIMD here. This is called automatic vectorization, and it's an open research topic. It's very difficult to get right. And in cases where it does get it right, it works quite well. But it's based on pattern recognition, which requires you to write your program in some way that the VM itself can detect, hey, here's a good opportunity to use SIMD. I don't think that's the optimal way to expose SIMD to the web. I think the optimal way is to really give you, the developers, the power to do it yourself and use these processors exactly as you want. So this brings us to SIMD and Dart, which consists of 3 new types. Dart has types. There is float 32x4, and that's just 4 32-bit floats packed together. There's a list of these, and this is, if anyone does WebGL development, there's float 32 array. This is the equivalent of that, but for SIMD values. And there's also UN32, which is just 4 unsigned 32-bit integers tucked inside of 128 bits. But the key thing here, and the difference between attempts at automatically adding SIMD to your program versus doing it in a way that you have control, is that you are given composable operations in Dart. You get to control how SIMD is executed, where it's executed, and when it is. So I've enabled arithmetic operations, logical bitwise operators, comparisons, reordering, shuffling. And I'll walk us through some examples of how you use this new functionality. So float 32 cross 4, you can think of it as split into 4 lanes, X, Y, Z, and W. And the operations that you can perform on float 32x4s are on the left, the standard arithmetic operations, square root, reciprocal, min, max, clamp, absolute values, all the things that you would want when you're doing anything numerical. And anything that is not directly there, you can build from these very simple composable primitive operations. So here's some code. So I have var a, Dart will figure out the type of a automatically. And I say new float 32x4, and I pass in the values in there. I get a SIMD 1, 2, 3, 4. There's also a constructor 0, which just gives you back the 0 vector. So how do you access these individual lanes and modify and mutate their values? So here we've constructed again our go-to vector, which is just 1, 2, 3, 4. And if we want to look at the lanes, we can just call a.x. It's just a nice accessor for each lane, .x, .y, .z, .w. But if we want to change one of the lanes, the values in the lane, we call a method on A called with X or with Y or with Z and pass in the value. And what that does is it copies A and replaces the X lane with the value 5 and returns a new SIMD value. That might sound heavy. I mean, it might sound like, oh, we're copying something and allocating a new object. But when the optimizer kicks in, none of that happens. It's all sitting in registers. It's all very efficient. So doing arithmetic is very natural. Constructed 2 vectors here, A and B. We add them. We add all 4 numbers at the same time. It reads very nicely. I mean, var c equals a plus b. It just happens to be using a SIMD unit behind. So let's look at a more substantial example here. So let's say we have a huge list of numbers and we want to average them, right? So the algorithm here is sum up all the numbers and divide by the number of values that you have. So here is the scalar version. So, for I is less than n, sum it up, and then divide and return that. So how do we turn this into a SIMD program? Well, it's not much different. It takes a float 32 cross 4 list. And again, we just sum them up in the inner loop. But at the end, we have to do this extra step because what we've actually done is we've computed 4 subsums. And we have to figure out the total sum as one final step. So everything up until this line is executing in SIMD. When we get here, we start using that VFP, that yellow piece of the CPU that we saw earlier. Before that, we're using the red part of the CPU. So diagrams help. So along the top, we have our long list of numbers. And what happens is we add all the blue numbers together. Then we add up all the green and the red and the yellow. And the adding of the different colored lanes happens simultaneously. It happens in parallel. This is a very limited form of parallel computation. So at this point, we're done executing SIMD code. But we've cut the number of instructions into a quarter, and we do our final step where we merge the results into a scalar value, which is the result of an average operation. So in this case, we end up executing 75% fewer loads, 75% fewer adds, and 75% fewer stores. Drastic cut, and we end up running 4 times faster. Minimal change in your code, and the new features in the Dart VM will make these algorithms run significantly faster. So this is the only slide with assembly on it, I promise. Although I encourage you to start looking at the disassembly from your JavaScript engine or the Dart VM because it's very enlightening. But see our inner loop here where we just do sum plus equals list I? When the optimizer kicks in, this becomes just a single load where we're loading the ith element of list and then just an add. It's all in registers. Nothing goes out to memory except the load, of course. So it really gets this optimal. You get to write this code at this very high level in this nice language like Dart at a high level, and then the optimizer is going to get it down to just 2 instructions. Yeah?
So you're talking about this Dart VM.
Mm-hmm.
In the presentation that we had before this, it said that the Dart stuff we were doing compiles down to JavaScript.
Yes.
Are you saying in this case that the code, the optimized code where you add that extra line of code actually runs with a VM that's inside a browser, and would all browsers don't have that VM, is that correct?
No, that's a great point. So Dart VM is a new VM that's experimental. So we've added it to Dart VM. In the case where your program is using SIMD and it's compiled to JavaScript, JavaScript lacks SIMD support, so we end up issuing 4 operations in sequence.
Okay.
And if you have a smart JavaScript VM like Mozilla's, it might end up replacing those 4 operations.
Are you saying that Chrome doesn't have this yet?
Chrome does not ship with Dart VM, no.
Okay.
No. Yeah. So let's look at shuffling. We have these lanes, right? And we want to be able to reorder the entries inside the lanes. And if you've done any WebGL programming, you're familiar with GLSL's shuffle syntax. Well, we have that in Dart, so it's really nice. So first we have our 1, 2, 3, 4 vector, and then we want to assign B to be X, X, Y, Y. And we get 1, 1, 2, 2. So that single line has just reordered these values, and it outputs a very optimal assembly code. And then we could do www, and it just takes the 4, 4, 4, 4, 4, or we could reverse the order of the entries in a SIMD register like this. So these are these composable primitive operations that you will use to build larger real-world applications from. So the tricky part with SIMD programming. Oh, was there a question? Yeah.
I think previously I saw that you had something like in order to set the value of the SIMD, you had something with a function call.
Yes. That is a good question, and it's a very detailed technical answer, so we could talk afterwards. But yeah, I know. It would be better. But you can't have everything. So let's look at this very simple function here, max. It just takes two values and returns the bigger of the two. And the code is obvious, right? If A is greater than B, return A, otherwise return B. Hey. But how do you do this in a SIMD world where all of your variables are actually storing 4 values? And this is where branching in SIMD gets a little funky. So let's say we had A as 1, 2, 3, 4, and we had B as 0, 3, 5, 2, 0. We said A greater than B. Like, what does that mean, right? Because the true maximum here is actually 1, 3, 5, 4, right? So you cannot just say, like, if A is greater than B, return A. It's a meaningless statement in a SIMD world. So you end up having to write a branchless version of your algorithm, which is kind of interesting. So I'll walk you through it. So here, this line here says, UN32 cross 4, typo, greater than is equal to A dot greater than B. And the reason that it's not the greater than operator is because it returns something unusual, so we wanted to make it explicit. And what it does is it returns this bit mask to you. So here we say A greater than B, and we get this weird bit mask that says it's all F's or all zeros, depending on the true or false value of the predicate that you just evaluated. So in this case, we see that 1 is greater than 0, so we get F. We see that 2 is not greater than 3, so we get 0, and so on. Which then brings us to the next line of the program, which is select, where we then take that mask, that 0, F, 0 mask, and we select between A and B. And what that ends up looking like is we say, okay, take the vector on the left and select the lanes from the column with F on it if the lane has F in it on the left. And then select the lanes with 0 in it otherwise. So you end up with the true lane-wise maximum of these two vectors. And this is how you would express this type of algorithm in a SIMD world. So it's a little bit different, but it's kind of interesting. There are no branches here, but somehow we've selected and gotten 2 different values, but we never have an if statement. So how does the VM optimize for SIMD? I've kind of touched on this already. It unboxes everything. So unboxing might be a new concept for some people. Typically, an object in a VM, when it's boxed, is allocated in memory, and it's this heavyweight object with like a class ID at the beginning and all of this extra metadata associated with it. But an optimizing VM will actually unbox the value and store it inside of a CPU register. And the second optimization that we apply is replacing method calls with inlined machine code. And that's why that inner loop looked so great. It just had the load and the add. That's because we've inlined all of the method calls like add and go and load this value from this array at this index. All of that gets replaced with just the single instruction that can express these concepts. And this also avoids method call overhead, so we don't have to go through the prologue and the epilogue of calling into and exiting from a function. So how much faster can things get with SIMD? So 4x4 matrix multiplication, which is a fundamental operation in 3D graphics and physics, gets about 3 times faster, which is it's pretty sweet. Bulk multiply, like an algorithm like the average, things like that, it can approach like 6 times, 5 times faster than doing it in scalar. And that's a trivial algorithm to port from scalar to SIMD code. 2 3D boxes, a Boolean intersection test, do they overlap? Gets about 1.5 times faster. As does vertex transformations and crack and blur, the exact algorithm that Mozilla is attempting to automatically detect and use SIMD for you. If you were to express it in Dart's SIMD types and primitive operations, you can get a 50% speed up, which is pretty sweet. So wrapping up, Dart SIMD has landed. It's in the VM now, so if you go and download like next week's release, it should be there. I put an asterisk there because what has landed is the new types and the new operations that you can perform on them. What hasn't landed yet is the optimizer, and that's coming in a week or two. So little pieces of the optimizer will be landing over time, and these algorithms that you write tomorrow will start to get really fast, just magically. SIMD lets you use your entire CPU. You execute fewer instructions, you get faster performance, you get longer battery life, and you get a better web. The Dart VM in general stretches the performance envelope, and it's going to make new magical experiences on the web possible. So why does SIMD matter? Again, here we are back at this console timeline, and we can do this. We can bump ourselves into the gray area between PS2 and PS3 and start closing the gap of what we can do in the browser versus what we can do on a video game console. Because if we want to be able to do this in the browser, and I do, we need SIMD. It'll never happen unless we start exposing these very powerful pieces of the CPU that just sit idle to us, the developers. So just one thing, I just want to talk about the definition of fast, because I hear a lot of people say, well, the web is really fast, JavaScript is really fast. I don't really agree. So this is a graph of Box2D benchmarks that was put up by Joel Weber on his blog in a December 2011 post. It's a really interesting post. I recommend checking it out. But it's comparing the performance of a 2D physics engine across all these different language runtimes. Down on the bottom is C. It's about 5 to 10 milliseconds per frame update. Up here, 20 times slower, that's the web. We have to collapse that gap and close it and bring it down. I mean, look at Java. Java is only about twice as slow as C, but we're 20 times as slow. We've got a lot of room to get faster.
All right, so thank you so much, John.
Yeah. Thank you.